Welcome to the third video of Discrete Mathematics. In this video, we're going to be looking at tautologies, contradictions, and contingencies. But first, let's look at rules of inference. Our first rule of inference is modus ponens. What modus ponens is saying is, if P is true, then Q is true. And P is true, therefore Q is true. The three-dot symbol means therefore. Modus tollens says, and this is, by the way, a good example of a contraposition, and I'll show why in just a second. It's saying if P is true, then Q is true. Q is not true, therefore P is not true. In the form of contraposition, we're looking at negation of Q implies negation of P. So, if P is true, then Q is true, but Q is not true. Q is not true, therefore P is not true. All right. And for addition, we have P is true, therefore P or Q is true. Basically, we're not factoring out the possibility of the existence of Q. Q can be true or false, but it's P or Q can still be true, but P is definitely true as a part of it. So both of these can be true, Q can be false, but P is definitely true in that one. Simplification. P and Q is true, therefore P is true. We can also say P and Q is true, therefore Q is true. It's just validating the proposition. Hypothetical syllogism. P implies Q, Q implies R, therefore P implies R. This is exactly the transitive property. So P, Q to R, instead of going one after the other, since they all have to just be true, we don't need to look at the middleman. We're just going to skip to the end, and we have P implies R, because if P is true, then Q is true. If Q is true, then R is true. So if this has to be true in both cases, then this would be true in both cases. Therefore, P implies R. Disjunctive syllogism. P and Q is true. P or Q, my bad. P or Q is true. P is not true, therefore Q is true. It's basically you're eliminating the P. Therefore, Q would have to be true because this statement has to be true in some form, and if P is not true, then Q would have to be true to make this statement true. And that's the same thing with modus tollens. In some sense, this has to be true in like its own world. Like if P is true, then Q is true. That is true. But since Q is not true, then P is not true. But if this wasn't the case, then this itself, the P implies Q, would be true. P is true, Q is true, therefore P and Q are true. That's pretty simple. And lastly, now we have resolution. P or Q is true, negation of P or R is true, but since we can't have both of these as a possibility, Q and R are true. Now, the logical operations under the tautology column validate every single rules of inference. And we're going to look at why these are validating it and why they're considered tautologies to begin with. We have 4 other rules of inference that I'm not going to get into, and those are universal instantiation, universal generalization, existential instantiation, and existential generalization. Tautologies. What a tautology is basically saying is, if we have a truth table for a logical operation, if the final column of the truth table gives us all true values, then it's a tautology. So let's look at one of our tautologies from our rules of inference. Let's pick modus ponens. P and P implies Q implies Q. Let's prove that this is a tautology by making a truth table in the tautology slide. So let's go back, and I'm going to write it down on the top first. I'm going to write P and P implies Q implies Q. This is what we're looking at. We have to prove that this is a tautology. So first, let's make our truth table. We have two propositions within the whole thing, so we're going to write P and Q. Oh, that's a bad Q. It looks more like an A. We're going to write P and then Q. I'm going to put them into their own columns. I'm going to extend this line as far as possible. I don't know how much space we're going to need. And then we're going to do the basic setup for P and Q. We have true, true. I have a true here and true here. And then we're going to have false, false. And that's our basic setup. And now we're going to make a column for P implies Q. Always go from the innermost parentheses and outward. So we'd have to look at this second and then the entire thing third. So we're going to look at P implies Q first. And we already know the rules. So true, true gives us true. True, false gives us false. False, true gives us true. And false, false gives us true. And then we're going to look at P and P implies Q. And for that, we're going to look at this column and the first column. And if both of them give us true at the same time, then it's true. So true. And the rest of them have at least one false. We have a false here, so false. We have a false here, so false. And we have a false here, so false. And lastly, we're going to look at the whole thing. So P and P implies Q implies Q. So we have to make sure that we're looking at it in the right order. So we're going to look at this column first and then the Q column second. So that could make the difference between true false and false true, which true false would give us false in a conditional statement and false true would give us true. So we have to make sure we go in the right order. So true true gives us true. False false gives us true. False true, we have to go in that order. False true gives us true. And false false gives us true. And all of these are ending up to being true. All of these got a truth value. Therefore, a truth value of true. Therefore, this is a tautology. They all got true. And the next one is contingency. This one is very straightforward. We could just use a basic conditional statement. Basically, what a contingency says is you need at least one true and one false in the final for the final results. So we have P, we have Q. I'm going to do P implies Q, and that's going to give us, well, let's do our basic setup first. True, true, false, false, true, true, false, true, false. We're going to get true, and then the second one is false for true false, and we can see here that we have at least one false, at least one true, and that makes it a contingency. It's as simple as that. So a contradiction is the opposite of a tautology. All of your end results have to be false in the last column. So let's negate that tautology that we had written down. So the negation of, oh, hold on, let's try that again. Hold on, the negation of P and P implies Q implies Q. We have to find the negation of that whole thing. So let's make a truth table again. And I don't think I'll be able to fit that last one in. So I'm just going to write the negation of this. Let's quickly fill in the truth values. We have true, false, true, true. Then we have true and false, false, false. And then we have true, 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 true. And now we're at the contradiction part. So the final results we get are all false, 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 and false because we're negating the entire tautology. We're negating the whole thing. So since all of these give us false, we can say that this is a contradiction. And that sums it up. Thanks for watching. Please be sure to like and subscribe. And the next video is going to be about proofs.